So I want to continue on looking at Kruskal-Wallis type examples. So this is multiple group comparisons using the non-parametric equivalent of the ANOVA test. So this next example I want to look at is some idea about sort of marine conservation. The context for we're talking about examples is around fisheries and whale stocks. So we've got this idea that how might we measure the health of some of our marine systems? Something is about getting an idea of the trophic level, the average trophic level. So we have this sort of hierarchy in our marine system. Have level 1, the plants and algae that generate their own energy from the sun. Then we have the different food chain going along all the way till we get to the apex predators at the top of the food chain. Now there's some idea that the high trophic levels have high economic value. So one way to measure the state of a fishery or an area is to see, well, how much of the high trophic level stuff has been taken out of the system. Right? That would be a sign if the high level trophic level fish have been taken out of the system. That could be taken as a sign that the system is under pressure, okay, or a sign of overfishing. So what's the context that we want to look at? How might we end up with a real world example that we might want to measure these sorts of things? Well, the example might be something as follows, where we've got introduction of different zones for our fishing areas. So we might have a strict no-take zone. We might have an area where we allow recreational fishing and most uses, but we restrict commercial fishing access. So it sort of could be called a buffer zone. It has most of the uses that we want, it has all of the uses except commercial fishing, and then the unrestricted areas for fishing. So that would be where the fishing fleet can operate. You can start to think about this and you can start to see that, collecting this data might be difficult. Sound a bit like a broken record saying that yes, in the natural sciences, it can be quite expensive to collect this data. So we might have some sampling strategy. We have to be out in the field. We have to get the boat out there. We have to get to the location. We might then have to, get out there and do this monitoring each day. So we've, got our sampling strategy. We've tried to make it random. We want to get a measure of the mean trophic level for each day in our 3 zones. So this is sort of what we're looking at here, something, very stylized representation of what we might have. We have the marine park area situated on a reef, somewhere where we might expect biomass to go. We've got some areas where we're allowing commercial fishing. We've got some areas where we're allowing recreational fishing. So we've got 3 different areas related to this system. And what we're doing is we're going out and we've got designed a sampling strategy. I think I said at 3 meters, 3 meter depth, relatively large sections, and we're measuring the biomass, or we're trying to get not so much the biomass per se, but we're trying to get a sense of the trophic level. So the different kinds of fish we observe in each of these sampling locations, and then we're going to add them all up and find the mean. Okay, so what might our data look like? Our data looks like something like this. So what is this? This is the mean trophic level for my NTZ. That would be my no-take zone. BUF would be my buffer zone where I'm allowing recreational fishing, and the free access zone. So this is commercial, this is everything goes zone. So for each of these different zones, I've got measurements on the trophic level. What do I do with them? The first step is to create a plot. Even though we're ultimately going to conduct a non-parametric test, we're still going to use our standard box plot. So let's have a look at what that looks like. You can see that it does in fact look like the no-take zone might be a little bit higher trophic levels than the buffer zone and the unrestricted zone lower. But just on that plot, it's not totally convincing. I guess the other thing that we might want to look at is here, the default plot or order in R is going to be fine for you to use. I've got no problem with you doing that, but sometimes we might like to order them. And if we ordered them as no-take, buffer, unrestricted, that might look a little bit more convincing that we might find some differences here. So if we look at the no-take zone and we look at the unrestricted zone, starting to look like, I'm starting to think that, yes, okay, maybe there is the no-take to the buffer to the unrestricted, that there is sort of a pattern emerging. We might not get some statistically significant differences, but this visual representation is giving me a good idea of, yes, I think that, I'm starting to get convinced that there's a good chance that the trophic level in the no-take zone is actually higher than in the unrestricted commercial fishing zones, and maybe in the buffer zone. Not sure about that either. To conduct our test, we're going to convert our raw data into the ranks. So this is what's going to happen in the background. All of this data, so we're going to find all of the levels, the trophic levels. We're going to rank them from highest to lowest or lowest to highest. Doesn't actually matter as long as you're consistent. So we're going to get 3 different rank orders for our data, and it's going to be the rank order of the data that is used to conduct our test. So not the actual values, but the ranks. Okay, so what's our test structure? Trophic level in all zones is the same. So again, nothing about means, just this general statement of a null. The alternate trophic level is not the same. So you can see I've started to change around sometimes the way that I express the alternate. Sometimes I say there is at least one difference. They're not all the same. You don't have to follow one, exact format, but it does have to be clear. All of those alternates have the same meaning. How do we implement the test? Well, we're getting quite good at this. We go with the data object that we read into R, apply the test. Measurements is the variable of interest, and factor is the grouping variable that I've got. I'm going to apply my p-value decision rule, and if I reject the null for the Kroskal-Wallis, I'm going to go on and conduct pairwise t-tests using the formulas that are pre-baked in R with the Holm correction to control the type 1 error rate. So we implement the test with the fish data, Kroskal.test, trophic.zone. And you can see I get a p-value that is less than 0.05, therefore I reject the null of no differences. It's as simple as that. You just need to read in your data, tell R which test to use, and then y tilde x. This is the grouping or factor variable, this is the response variable or y variable. Because we have rejected the null, we would then proceed on to pairwise equivalent of pairwise t-tests. So how do we do that? We have fish pairwise.wilcox trophic zone. And this is going to conduct all of the comparisons that we want to conduct. You can see actually here, they are all different. So we end up with the buffer zone is in fact different to the free zone. The buffer zone is different to the no-take zone. And the no-take zone is different to the free commercial zone. See, from my visual inspection, that was the only one that I was feeling particularly confident about. I was pretty sure that the no-take zone and the free commercial fishing zone would have been different. The other two I was actually a little bit uncertain, but we've seen that we have found some differences. Again, whenever there is a tie in the data set, ARC generates warnings. Warnings we don't have to worry about. They're a warning. It doesn't mean that something is definitively wrong. So what's a summary of our non-parametric methods? When do we use them? Small data sets from a non-normal population. Okay, if we had a small data set from a normal population, we would still be better off using the ANOVA. We work with the ranks, that's the main advantage of these, or the main method. Rather than the actual data, you use the rank order of the data. The advantages are that they require few assumptions. The disadvantages are if you use these methods, you have less chance of detecting a difference if a difference truly exists. So they have less power than parametric tests. So if parametric tests are valid, you would always want to use them. The catch is that if the assumptions of the parametric model are not valid, then it would be inappropriate to use them. Hence, you need to use something like a non-parametric method. And that is an opportune time for a break.